just wait for me to turn it to the next video.
So it seems like we don't have enough to talk about only in the context of zero knowledge, that we need to add all kinds of signatures and FHE and stuff, how it combines with zero knowledge. That was a joke, by the way. All right, are you plugged?
Hello, hello, yeah, okay. Hello, I'm Stefanos. I'm a PhD student at Imperial College London, and I'm also a security researcher at ZKSecurity. And today I'm going to present a joint work with Dennis from Input Output, and Ben, who is my advisor at Imperial, and he's also working at Eclipse Lab. So this talk is going to be a bit different than the rest of the talks because we take as granted that ZKPs that we are using are secure. The circuits we have written are secure, everything works fine, the trusted setup, if we needed one, is safe. And the question we want to address is what else we need to do so we can utilize the nice properties that zero knowledge proofs give us, and we're going to focus in blockchain rollups. So why do we need blockchain rollups? Basically to scale blockchains. There is an intuition of a scalability trilemma. Maybe it's outdated, maybe there are better L1s that can solve scalability, but for blockchains like Ethereum, what we do is we build layer 2 blockchains that are basically completely independent blockchains that perform all the computation off-chain, meaning in the layer 2, and they claim that they inherit security by publishing data on an L1 and verify the correctness of the execution of L2 transactions in the L1. So at a glance, what happens in a rollup is that we gather a lot of transactions in the layer 2, we create a rollup block, and then we batch together a number of rollup blocks in a rollup batch that we are going to post in our main blockchain, in this case Ethereum, and there we will have our data availability in Ethereum, and we will also verify the correctness of the execution of the L2 transactions in the layer 1 blockchain. So what a ZK rollup does is that it performs the execution, meaning the processing of L2 transactions off-chain, basically, and verify them on the L1. It uses zero-knowledge proof, or let's call them validity proofs, because they don't use the ZK property, which are basically cryptographic proofs that assure the correctness of L2 state transitions. The benefit of using cryptographic proofs rather than more optimistic approaches like fraud proofs is that you have faster finality, because the moment you verify your proof in the L1 and that L1 block gets finalized, then you can say you have finality for the L2, and also you can have better compression. And the key roles that a rollup has is a sequencer, that in most rollups at the moment it's a completely centralized component that we trust blindly, that orders transactions in the L2 and batch various L2 blocks into a batch that will post in the L1. We have a prover that generates validity proofs for the that proves the correctness of our state transitions, and we also have an L1 contract that basically verifies proofs in the L1 and keeps a canonical order of finalized states of the L2 blockchain in the L1. Here is a diagram that demonstrates those three components and how a user can interact with them. You can observe that the user has two options: one to send a transaction to the L2 sequencer, and one to force its transaction to the rollup contract, and we are going to explore that concept in a bit. So in the rollup world, we had some incidents. I would say benign incidents where, for example, in the blast rollup, there was a very quick upgrade to censor an attacker's address. And in the linear chain, there was an incident when block production stopped for a while, so they can blacklist some compromised addresses. Although those are benign cases, that's something we don't really want to happen in a blockchain, even if it is an L2 blockchain. What are the main takeaways? Is that L2s are completely centralized and can lead to censorship, so you are not inheriting censorship resistance from the L1. And what that means that we need a mechanism to force transactions through the L1 and also to have a way to safely perform upgrades. And the intuition for those mechanisms is that L2s should indeed inherit L1 censorship resistance, but also user funds should be as safe as they are in the L1. And to give you more intuition of what does that mean is like the main blockchain vulnerability, it's not like reentrancy, it's not like issues in consensus, etc. We have the most losses of funds due to multisigs being compromised. And an L2, it's basically a multisig in the L1. So if we don't have some more advanced mechanisms, that means that all user assets in the L2 are in risk if the multisig is compromised. So the contribution of this work is that we provide a formal model of validity-proof rollups via Alloy. We model 3 key mechanisms, which are first Q, that ensures a user transaction can't be censored. Safe upgradability, which means we can perform upgrades safely, and we will explain more what that means. And safe blacklisting. So in some cases, in those L2s, we might actually want to do some censorship for various reasons, but we want to still keep some basic properties for the users, and we will see how we can achieve that. Yeah, and the main goal is eventually to provide stronger guarantees to users that what they use indeed is close to L1's properties. So our security assumptions is, as I mentioned in the beginning, that validity proofs are correct and safe. And our model is that the sequencer is completely malicious, we don't trust him. The admins, meaning the multisig, can be compromised. There could be malicious users that try to DOS our systems. And we also have like one more assumption that the L1 is trusted and secure. So our goals is to provide weak liveness to users, meaning that if L2 finalizes new blocks, then user transactions will eventually be included. The second property is that upgrades should be performed with a safety mechanism, means that users have the opportunity to exit before an undesirable or malicious upgrade is enforced. And finally, we don't have retroactive censorship, which means that once forced transactions are in the queue, then we cannot blacklist them, we cannot censor them, we must process them. And we will see why that is important. So what is Alloy and why we use it? Alloy is basically a first-order relation logic that is useful to describe system states and operations. It has a SAT-based engine that finds counterexamples in a bounded state, meaning that basically it performs bounded model checking. And it's really handy for performing protocol-level logic verification. In this work, we don't actually verify source code, but we analyze the correctness of mechanisms that are used by rollups. So let's begin and describe our model. We have inputs, which basically represent transactions submitted by end users. We have blocks, which are ordered sequences of inputs. Then for commitments a commitment is basically when the sequencer commits that it will create a proof for that batch, and the proof is the proof for that commitment. For both of these, we keep track of the state, which is the existing state of the rollup, and a diff, which is what we commit or for what we create a proof. And we also have in the L1 our contract that models basically the L2's representation on the L1. So what is the state of the L2, what commitments we have, what proofs, etc. So here is the Alloy code. Alloy basically it's a declarative language, so it's pretty easy to understand and follow. And we explain a lot in details how to use it in our paper, but also we have some source code available that I will give you a link in the end of the presentation. So we start with a very naive rollup model, which is actually kind of what most rollups are at the moment in production. And the only thing that that rollup does is it has a process function that actually enforces proof and commitment matching and basically verifies ZKPs in the L1 and progress the state of the L2 in the L1. So what are the issues? There is no first queue mechanism and there is no safe upgrades mechanism, which can lead to vulnerabilities to censorship and malicious upgrades that could basically get all user funds out of the L2. So let's start with our first, and I will say most important mechanism, which is the first queue mechanism. It's a mechanism that almost all rollups want to implement. So we have force inputs that are posted on the L1, and those inputs must be included in the next finalized block if the L2 wants to progress. So there should be, in other words, some progress in the queue if the queue is not empty and we want to create a new and finalize a new block. What we guarantee, and it's a FIFO queue, and what we want to guarantee with that is that user transactions cannot be censored. So let's see a bit more formally what kind of properties we need to define in Alloy to achieve that. So we have guaranteed processing, which basically means that if the first queue is not empty and a new state is finalized, then the head of the queue must be processed and removed from the queue. And here is an Alloy fact basically on how you can do that. And we have always, and then we say if there is something in the first queue and the next finalized state it's different than the existing finalized state, that implies that the first transaction of our queue is in the new finalized inputs, and that the first transaction in our queue, it's not the first transaction in the next state of the queue. We also have like some more properties. The first one is that the first queue should be stable, which basically means if the finalized state did not change, then the first queue did not decrease. Another one, it's kind of a symmetric property, state invariant, which means that if the first queue is not empty and did not change, then the finalized state remains unchanged. And then we have that first inputs must progress, which basically means that when the first queue progress, all elements in the queue, all inputs in the queue should progress. And we have order preservation, that we are not able to actually change the order of the inputs in the first queue, and finalization confirmation, that if an input was in the first queue and then disappears from it, it was finalized. So let's move on to our second mechanism, which is secure blacklisting. And the dilemma that here L2s might have is that they might want some optional blacklisting for compliance reasons, or because those L2s are operated by some companies and they might have some policies. But the blacklisting can actually freeze the first queue, so we cannot make progress in the L1, given the previous mechanism of first queue we described previously, that we can't change its properties. So the solution is either to allow blacklisting to be applied after or during times that the first queue is completely empty, or to require blacklisting changes to go through the first queue, or an upgradability mechanism that we will explain later. So let's move to our upgradability mechanism. And basically how that works is that you should announce the upgrade on the L1. Then you should have some timeout window that allows users to submit transactions to the first queue if they can't, for example, exit through the L2. So they should have some time that they can include their transactions in an L1 block. And then what is important is before you deploy the upgrade, you should process all first transactions in the queue. And the result of that is that we ensure that no user is actually left behind with block first transactions at upgrade time. And let's move on to two examples. I will start with the second one. So the most common approach in Rollups is to just have a naive, I will call it, a time-based upgrade, where you give some time for users to exit your L2 before you perform the upgrade. The problem with that is that someone can DOS the first queue. For example, if a malicious entity wants to perform a malicious upgrade and stop accepting exiting transactions in the L2, then it can also DOS the first queue in the L1. And after the timeout happens, if we don't empty the first queue by processing all the transactions, then some users will stack in our rollup, and they will not manage to make it before the upgrade is performed. And another common mistake we identified is that if we can enable immediate blacklisting, given that we have a secure first queue mechanism, then the L2 will get stuck. So what Alloy does is that with the facts we define in Alloy, it will create counterexamples that show how the system can break. So here it's the blacklisting example. And basically what we have here is that we start with an empty state where everything is basically empty. We have first queue which is empty, blacklist, which is a policy for blacklisting, which is empty, and ongoing upgrade, it's none. We include an input in the first queue. So now we have an input in the first queue, the blacklist is empty, and ongoing upgrade is empty. Then we announce an upgrade policy that basically blacklists the input one. And we have a timeout that for that policy, the status currently is false. And in the next step, basically we change the status to true. And what happens in the end is that the first queue now has input one, the blacklist has input one, and remember the rules we had in the beginning of the presentation. Now we cannot make any progress. So that's how Alloy will try and find counterexamples that are pretty useful to understand what is working in our system and what not. So we basically Alloy does bounded analysis, right? So you set a limit of how many steps it can perform, and then it tries to do model checking based on that limit. The hypothesis here is that many design flaws in protocol design appear even in small examples. So you need not that many steps to find all the issues. Here are basically the numbers when scope is 5. So lines of code is independent of scope. So the simple, very basic rollup model was written in almost 300 lines of alloy. And then the simple model with the first Q mechanism was written in 500 lines. If we add blacklisting, is 700, and then with upgradability, it's close to 1,000 lines of alloy code. And then we can use the solve time for scope 5. What we observe is that we can go for, like, in a laptop, we can go up to scope 9 to 10. After that, basically, alloy will not manage to solve our model for the most complicated ones, meaning the upgradability. Okay, so what we presented is that an alloy model that basically we can use to verify that the properties we want in a rollup actually hold, and indeed the rollup inherits some properties from the L1. What is an important takeaway is that when we use ZKPs in general, we typically integrate them in some broader system. So we must understand what the ZKPs provide. In this case, they provide validity proofs. So, and then we need to design our system to correctly use the zero knowledge proof. And because of the very strong properties the zero knowledge proof give us, we should make sure that the rest of the system also enforce what the system should do. And in that case, we did it with alloy. So in the rollup context, what we did is we manually checked the implementations of the rollups and tried to encode everything manually to alloy models, which might be not that practical because we don't verify the source code. So one option could be like to go from source code to alloy. Another option could be to go from alloy to source code, to smart contracts, basically, that enforce everything. Both options, although could be possible, require a lot of effort, and you might introduce various bugs trying to implement them. So what we actually propose is a pragmatic approach where you have a design spec written in alloy, and from that design spec, you have verify some critical properties, and then you can use those critical properties that you know are correct through bounded model checking to use them for performing formal verification or even property-based testing of the actual implementation. And something else we need to do for rollups is basically to add in all of that security councils and how those could affect our analysis. So you can find our paper in archive, and also you can find all the alloy implementation in that GitHub repo. So that was it.
Thank you very much. Do we have any questions? Any brave one?
Thank you for the presentation. And I was wondering, the competitor to ZK Rollups is optimistic Rollups, which introduce a lot of complexity due to handling fraud proofs. Do you think your approach would generalize to those?
So that's a very good question, and we tried to tackle that, but it turns out it becomes way more complicated because with fraud proofs, much of the logic goes actually to your smart contracts in the L1 that needs to also implement fraud proofs. So we would have to basically model the fraud proofs in alloy, which makes it a way more difficult task to do. And the nice thing about using zero knowledge proofs is that, okay, you can assume are secure, and then the only thing that happens in the L1 is that you verify a proof, and that's it. So it's way simpler to model a system that uses ZK rather than an optimistic approach that requires more logic.
Any other questions for our speaker? All right, let's thank the speaker again. Thank you very much, Stefanos.